All right, let's jump right in. Today, we're going to be mathematical detectives. We're on a mission to crack the code of polynomials and uncover their biggest secrets, the things we call zeros. So let's get this investigation started.
You see, every single polynomial out there has a secret hidden inside of it. And by the time we're done here, you are going to know exactly how to find it. Ready to become a math detective?
So what is this big secret? Well, it's called a zero. And a zero is just a special number you can plug in for x that makes the whole polynomial equal 0. You can kind of think of them as the roots of the equation. They're the fundamental points we're hunting for.
Okay, every good investigation starts with the most obvious evidence, right? The visual clues. And when you've got a graph of a polynomial, finding its zeros is actually super easy, as long as you know where to look.
Let's start with the evidence right here. Find the graph labeled number 4 in that bottom row. See that horizontal line? That's our x-axis. Now, the secret is unbelievably simple. Just count how many times the curve crosses that line. So for graph number 4, how many times do you see it cross? Yep, you got it. 2. The curve crosses the x-axis in exactly 2 spots, and that tells us this polynomial has 2 zeros. Every single one of those intersections is a solution we're looking for. It's really that simple.
Okay, feeling good about that? Let's try one that's a little trickier. Look at graph number 5 on that same slide. This curve, you'll notice, is a bit more complicated. It goes up and down a few times. But the rule doesn't change. So how many times does it cross that x-axis?
4, that's the one. 1, 2, 3, 4 different points. That means this polynomial has exactly 4 zeros. It's a fantastic simple rule, right? The number of times it hits the x-axis is the number of zeros it has.
But what happens when we don't have a picture to look at? We can't always rely on visual clues. Well, that's when we have to pull out our algebraic toolkit and, force the polynomial to give up its secrets.
The whole process is basically a straightforward 3-step interrogation. First, you take your polynomial and you just set it equal to 0. Second, you break it down into smaller, simpler pieces by factoring it. And finally, you solve for x in each of those little pieces to reveal the zeros one by one.
Let's see how this works in action. Our suspect is the polynomial x squared minus 2x minus 8. As you can see in the solution here, the first thing we do is set it to 0. Then we factor it, breaking it into 2 parts, x minus 4 and x plus 2. Now think about it. For their product to be 0, one of those 2 parts has to be 0. So if x minus 4 is 0, x has to be 4. And if x plus 2 is 0, x has to be negative 2. And just like that, case closed. The zeros are 4 and negative 2.
So, we've found the secrets. We cracked the code. But this is where the mystery really gets interesting. Is there some kind of hidden connection, a secret formula that links those zeros, the 4 and the negative 2, back to the numbers in the original polynomial?
Oh, you bet there is. We're about to uncover the secret formula that connects a polynomial's zeros to its coefficients. The numbers out in front of the variables. This is the master key that's going to unlock this whole thing for us.
Just look at this. This slide lays the proof out right in front of us. That top row shows the direct math. 4 plus negative 2 is 2, and 4 times negative 2 is negative 8. Easy enough. Now look at the second row. For our polynomial x squared minus 2x minus 8, the a is 1, b is negative 2, and c is negative 8. The secret formula says the sum of the zeros is always negative b over a, and the product is always c over a. And when we plug in our numbers, we get the exact same answers. It's a perfect match. This thing actually works. Okay, this is the ultimate test of our detective skills. If this secret formula works one way, it should work in reverse, right? So what if we're only given the secrets, just the sum and the product of the zeros? Could we use those clues to rebuild the original polynomial? Let's find out. In this last part, we get to be the architects. We're going to take the clues, the sum and the product, and use our master formula to build the polynomial from scratch.
Okay, here's our first set of clues. The sum of the zeros is 1/4, and their product is negative 1. We know the sum is equal to negative b over a. So, negative b over a is 1/4. Well, the simplest way for that to work is if a is 4 and b is negative 1. Now for the product, c over a. We're told it's negative 1. If we already know a is 4, then c must be negative 4. We put our coefficients a, b, and c together, and what do we get? The final polynomial? 4x squared minus x minus 4. We've totally reconstructed the code.
Now, this next example is really cool because it shows just how powerful this formula is, even with kind of weird clues. Here, the sum is 0, and the product is the square root of 5. Well, since the sum, which is negative b over a, is 0, that means our b coefficient has to be 0. If we pick the simplest value for a, which is 1, then the product, c over a, tells us c must be the square root of 5. And the polynomial? It's just x squared plus the square root of 5. It works perfectly every time.
So there you have it. We have cracked the code for finding zeros on graphs, we've done it with algebra, and we've even mastered the secret formula that connects everything together. But we've mostly been looking at quadratics, polynomials with an x squared, and that leaves us with one last big question. Does this secret connection hold up for even more complex polynomials? Now that is a mystery for another day.